Very good. Yeah, looks good here as well. Hello, everyone. Pleased to welcome Professor Falk Herwig. He's from UVic now, but he got his PhD in 1998 from Kiel University. And his initial PhD topic was on asymptotic giant branch stars, which are late stage, evolved stars. And he studied intermediate mass ones. He's branched out a lot since then, and you'll hear some of that as he gets going. He's in 3 major collaborations. One is called PPM Star. Hi. No worries. Yeah. Which is an effort to create a very sophisticated 3-dimensional hydrodynamic code for purposes of stellar evolution, which is maybe we'll hear a little bit about that. And then NuGrid and CanPan, which are all about nucleosynthesis and nuclear physics and how to get laboratory nuclear physics into astrophysics. And thank you for joining us, Professor. And the title of your talk here is The Dynamic Origin of Elements in Stars from the Early Universe. And we're going to interrupt if we have questions. Is that all right?
Oh, that's absolutely fine. Yes, great. Thanks for having me. And before we start, can you see my pointer?
Yes.
And is it reasonably visible, right? And then also if I do say annotate, for example, because I want to draw something, you see this, right?
We do.
Like this, for example. Great. Excellent. All right. So welcome everybody to the colloquium. And it's really a pleasure to have prepared this talk for you and to tell you a little bit about nuclear astrophysics, nucleosynthesis, the origin of the elements. And I'm going to explain to you a little bit our current research on trying to understand the anomalous abundances in metal poor stars. So these are stars that formed in the early universe that tell us something about the peculiar ways how nature can make elements. And sort of I will finish by sort of the highlight of the talk at the end is really sort of a new realization that we had a couple of weeks ago, finally sort of resolving a problem that has been really bothering us for several years now. And so we're writing a paper about it, and we think that this is a really key result that we feel personally very good about. And when I say we, there is a whole bunch of people involved in this research. My colleague Pavel Denisenkov here, students, of course, as well. And it was mentioned, Guy said already, there's several collaborations. These multi-physics, multi-messenger research endeavors require collaboration, and you can find on our webpage all the people who are involved. Okay, so let me clear these drawings and then move on to, oops, if I can, how can I cannot advance right now, let's see. Oh, this is okay, I can't have the annotation at the same time. Okay, so what am I going to do? I'm going to tell you, so I do not assume that you all took my stellar physics class last year, and so I will give you a fairly thorough introduction into the key points of how the elements are forming. And apologies to those who actually did take a recent stellar physics class or are researchers in this area. I'm trying to get everybody on the same page. And then we'll talk a little bit about these bizarre abundance patterns in the most metal poor stars and why they are anomalous. And then why existing theories that I explained in point 1 are insufficient to explain those observations. And then what are the new ideas that we have developed? And what more generally have we learned, therefore, about how the elements form in stars and stellar explosions, right? So that's the plan. Okay, so I'll start with this view. This is, as you know, of course, the chart of isotopes in its full beauty. And I'm teasing the observers sometimes. The observers, unfortunately, astronomers observe elements, and so they usually would show the periodic chart that chemists use. But we have an advantage as nuclear astrophysicists. We have much more fun, as you can see. Here are all of the elements in the Y direction, and I have highlighted some because the fonts are too small. There's lithium, fluorine, oxygen, iron, and then lots of heavy elements, europium, barium. And as you can see, each of these elements has many isotopes, and a key point in this diagram is that the black ones are the stable isotopes, but there are, of course, unstable isotopes, the radioactive isotopes on the neutron-rich and on the proton-rich side. And all of these elements have formed in stars and stellar explosions by a process called nucleosynthesis. And nucleosynthesis is that each of these little boxes here, shown one here in the schematic way, can do one of about 12 nuclear reactions. And some examples are given here. For example, if this was, let's say, carbon-12, it could capture a proton, or it could, and then release a gamma, and it could capture a proton, release an alpha, alpha, gamma, alpha, p, alpha, n. These are all reactions. And so here are 2 examples shown. And so you can think about what the red arrow would represent. And I'll give you the answer right away. It is a p alpha. And so how does it go? Remember, in the chart of isotopes, neutrons go to the right, protons go up. So what this means is we're capturing a proton. So we go one up, and then we release an alpha. So we go 2 alpha particles, has 2 protons down, 2 neutrons to the left. So this red arrow marks a reaction, a transformation of p alpha reaction. That would, in this case, we'll see an example in a moment, like nitrogen-15 p alpha is a famous example, nitrogen-15 p alpha, carbon-12. So now you can think a little bit. If I were here, I can't see you well enough, but I give you a moment to think about what is the green reaction. It is listed on this. So who wants to say what the green reaction is? Anyone? It is one of these here. So it is multiple choice.
Alpha gamma.
Alpha gamma is my guess.
It is not alpha gamma.
Oh,
So if we capture, yes, correct. If we capture an alpha, we go 2 neutrons to the right and 2 protons up. But then there's an exit channel, which is a neutron, so we go 1 back. And the famous reaction that represents this case is carbon-13 alpha N, and that is actually the reaction how neutrons are made in stars. Okay, and neutrons are really important, and we need to, are really important. So you get an idea of what how the nucleosynthesis works. Now, the key point here to remember with this view is that here is iron, and most elements, most isotopes are heavier than iron. Okay, so if you only live in a world where you worry about hydrogen to iron, you're really missing out on a lot. Okay, so now let's maybe go through a quick example, and that is the CN cycle for hydrogen burning. And that is one of the key mechanisms how hydrogen burning works, for example, in the main sequence. It uses pre-existing carbon-nitrogen isotopes to produce helium out of 4 protons. How does it work? Well, we start with, for example, carbon-12, and this is, now you know, this is a proton capture, a p gamma reaction. Now, this is an unstable species, nitrogen-13, with a half-life of 9.96 minutes, and it will decay to carbon-13. And then carbon-13 will capture another proton. Stable nitrogen-14 captures another proton. Oxygen-15 decays to nitrogen-15. And here comes nitrogen-15 P alpha back to carbon-12. And the net result of all of these reactions are that we're capturing 1, 2, 3, 4 protons, and out comes in the exit channel 1 alpha. So the net result is we have taken 4 protons and we made 1 alpha. That's the CN cycle, and you probably have heard about it. The key is here, nitrogen-15 could have, of course, done also a P gamma, and it does with some probability, but it is more likely to do a P alpha, and so that is a dominant cycle. There is another cycle going that way, and that's where the nuclear physics comes in. Which of these reactions take place is due to nuclear physics, nuclear reaction rates that are either measured or theoretically determined. With these so-called charged particle reactions, there are different burning stages, and you've probably seen something like this. This is a list of all of the burning stages: hydrogen to helium. There's reactions that form helium into oxygen carbon. Carbon produces neon magnesium, neon oxygen magnesium. So here is the products. There's secondary products. There's time scales. And so this leads to this onion shell model, in this case, of a massive star that ends with iron. That's the key. When the massive star evolution has reached the iron core, then it's over and the massive star explodes. And so the question is, first of all, why is it that this sequence of nuclear reactions ends at iron? And how are the other elements made? And the reason why it ends with iron is a very fundamental nuclear physics reason, which is that if you plot the average binding energy per nucleon, it has a peak at iron. So from hydrogen to iron, if you put 2 heliums together or 2 carbons together and you get, say, magnesium-24, the binding energy per nucleon of 1 magnesium-24 is smaller than the binding energy per nucleon in each of the 2 carbon-12s, and the difference is released as energy available to the star to prevent its further collapse. And so these up to iron, the fusion reactions are endothermic. Are exothermic, right? The reaction release energy, but beyond iron, they would be endothermic, and so they don't happen. But then how do we make all of these elements like zinc, silver, gold, barium, europium, lead, molybdenum, all elements that you've heard about? Well, the answer is, actually, let's look. We can figure out the answer by looking at something very simple that is known for quite some time. Actually, we can figure out the answer by just looking at the solar system abundance distribution. What you can see here is Anders and Gervais, 1989, known for a long time, on a logarithmic scale, normalized to something. We see here the solar abundance distribution, okay? And so what we see, generally speaking, is that by number, most of the elements in the solar system are are up to iron. Hydrogen to iron are the most abundant elements, but there are lots of these heavy elements, like lots of different types of heavy elements at much lower abundances. But the key point is that if you look carefully, there is structure in here. There is overabundances, small peaks at xenon and barium, at platinum and lead. And there's actually, if you plot it correctly, there's also there's a little relative peak here at germanium and strontium. Okay? And so what we say is that as a function of mass number, we find just by looking at the solar system abundance distribution that there are, in the trans-iron elements, there are 3 peak structures. And what is really important is these are double peaks, right? They're not single peaks, they're double peaks. And that is a key piece of information which reveals, and actually did reveal, to Burbage, Fowler, and Hoyle in 1950, in the early 1950s. So we know this for quite some time, but revealed how these elements are made. And the only thing that we need to know in addition to this is a little bit of nuclear physics in the form of the chart of isotopes. Now here I have zoomed in again in another region of the chart. And I have zoomed in actually to one of these regions. If we go back here, one of these peaks, we call it, is the second peak, is where xenon and barium is located. Okay, now you see here is xenon, and there is barium. Okay, and then you see a second line here. It turns out that for neutron number 82, you see a heavier outline here. And what the chart is indicating by that n equals 82, the neutron number 82 is special. And what's called, it's called a neutron magic number. And you have to think of it similar to, if you remember your chemistry class, there is something like closed electron shell. And if the electron shell and the chart of periodic chart, the elements with a closed electron shell are all in the last main group, right? They're all on the right side. And these are elements like, well, helium, neon, argon. These are elements that really don't want to react because their electron shell is closed. And this is the same principle in nuclear physics. Nuclear physics, at the end of the day, we have a many-body system out of many nucleons. They are interacting with their complicated quantum wave functions. We don't know exactly how. It's difficult, especially for species with such high numbers. But what we do know is that when the neutron number is 82, there is something equivalent to closed electron shells. And as a result, the N-gamma cross-sections, the cross-sections capture further neutrons is reduced compared to a little bit further left and a little bit further right. And what happens is that xenon here is a little bit further to the left. You see this is 26% of xenon 129, 26% in the solar system xenon 132. So in order to create a peak here, you need to have a flux from N-gamma cross-section of neutron captures that is going along here. It is hitting the n equals 32 where it is stopped. This is like a barrier. And from there, it would decay backwards when sort of the neutron burst is over to the region of xenon. Whereas if you have a much smaller neutron density where neutrons captures happen slowly compared to the beta decay, you follow this value of stability very closely, and you are hitting the n equals 82 at barium 138. And so the idea here is shown in this photograph of one of my classes on the chalkboard, where you're creating sort of two peaks, one by a neutron capture regime where the beta decay is long compared to further neutron capture timescales. That's the rapid neutron capture process. And you have another regime that is, so you're just going way out away from the value of stability until you hit one of these closed neutron shells, and then you decay back, creating this peak. And the other regime is a slow neutron capture process where you're following the value of stability, and you have the peak right where the n equals 82 intersects with the value of stability, which is around barium 138, lanthanum 139, cerium, and so on and so forth. Okay. So you can see how just by looking at the chart, the solar system abundances, and by looking at the chart of isotopes, we can understand this double hump picture. And so the notion that the elements are produced, the heavy elements are produced by two processes. The heavy elements, the slow neutron capture process, and the heavy and the rapid neutron capture process is long established and well tested in astronomy. Okay, so we have these two processes. S process follows the value of stability because the N-gamma cross sections are, the neutron densities are small, and N-gamma happens slowly compared to beta decay. Whenever an N-gamma happens, we're immediately beta decaying. Rapid is we have so many neutrons, like a burst of neutrons, say, for example, a neutron star merger or a supernova explosion, where we're having neutron captures piling on top of each other. We're going way out to the away from the belly of stability. Okay, so we can use this sort of concept of two neutron capture processes, R and S, by deconstructing the solar system abundance into elements that are dominantly produced by S process and R process, and those that are dominantly produced by R process. Okay, and the reason is that sort of this R process decay coming from way out here is somehow shielding, for example, xenon 138. If there is an R process contribution, all of the xenon 130, all of the species on the isobar 136 will remain here, and barium 136 is an element that can only be made by the S process. It's shielded. Okay, so we can have individual isotopes here that we can label as S only, as R only, or maybe produced by S and R, and by carefully comparing models and the solar system abundance and meteoritic information about the isotopic abundance distribution, we can figure out in ways that would be another 2 or 3 colloquia, like what the elemental breakdown is. And so you look at this table and you realize, okay, barium we find is 85% made by S process, by the slow neutron capture process. Likewise, lanthanum has a large S process contribution, whereas elements like cesium or xenon are really dominantly made by R process. Also, europium, silver, gold, iridium, and osmium are typical examples for R process elements. Okay? So now that you understand how the heavy elements are made, the neutron capture elements are made, I need to remind you of one thing. When we look at the solar system, we are really not looking at the result of one neutron star, one supernova. It is a total misconception that the elements are made in supernova, so we just had a supernova blow off and the supernova makes the solar system abundance distribution. Nothing could be further from the truth. The reality is that the study of galactic chemical evolution tells us that there are numerous objects, different types of processes that are all contributing to like supernova type 1a binaries and white dwarf black hole neutron star mergers and winds of AGB stars, LOMA stars. There's numerous processes that are contributing to the intergalactic gas out of which the interstellar medium out of which dense molecular clouds form, out of which stars form, which then again produce new elements. So there's a cycle of galactic chemical evolution which goes around and around. And in the solar system, what we're really seeing after, in a typical sun that formed in an evolved, mature galaxy, we're seeing the contributions of many, many different processes. And there is we can consider the solar system as sort of a representative mix of all of these different things that happen. And the more likely things are probably imprinting themselves more, and rarer things are just not playing so much of a role. Okay? With that in mind, I want to introduce the concept of an anomalous abundance. And an anomalous abundance is, well, what do we mean by anomalous? Well, the only thing that we really know very well and that we consider pretty normal is, of course, the solar system, right? And the abundance is in the solar neighborhood. And so when something is not like the sun or the solar system, we say, oh, it's different, it's anomalous. And astronomers have a way to highlight that, which is extremely useful, and that is called the bracket notation. And the bracket notation is essentially saying, take the ratio of two elements in the star and take the ratio of that to the ratio of the two elements in the sun and take the log of that ratio. And what that tells you is if that ratio is 0, so no, if the bracket notation is 0, then the star or the object that I'm looking at has the same ratio of these two elements than the sun. So the bracket notation of 0 is sort of normal. That's sort of like the sun. It might be that both elements are a factor 10 up or down because maybe of galactic collision instead of earlier, but the relative contribution of different processes would have been similar as in the sun. And you can see this here. I'm just giving you one example here. This is a paper that we had a couple of years ago where we looked at one of these metal poor stars. So this is a metal poor star which has Fe over H minus 1.6. So the iron over hydrogen abundance is about 20, 30, 40, 50 times smaller than in the sun. So it's a metal poor star, not very many metal poor, but it's quite metal poor. And so you can see here the abundance distribution shown in these two ways. One, as I showed you before, in this absolute logarithmic scale of number abundances, and the other in the bracket notation. And first of all, you notice that in the bracket notation, the dynamic range is much smaller because everything is normalized to the solar system. And we can easily see things that are near 0 or at least sort of similar. Two ratios that are similar mean that the ratio of those elements are similar, right? But everything sort of not too far away from 0 is like in the sun. And what we can see in now this happens to be a star where we try to interpret it with a couple of with a combination of this R process and this S process and the typical signature. And you can see here, the R process contributes in certain areas, the S process in other areas, and you know why? Because of these different places where the flux with R or S would hit the n equals 82, for example. But there are some features here that really could not be explained. And specifically, it's the arsenic to germanium ratio. Here you see arsenic, here you see germanium, and you just glance at it. You subtract these two values, and you can see that the arsenic to germanium ratio, a division in log is just a subtraction. It's 0.9. What this means that the arsenic to germanium ratio is 10 times larger in this star than in the sun. This must mean that something unusual has happened, something that does not happen all the time, because if it would happen all the time, the sun would have that ratio. So the bracket notation here really picks out something that is unusual. And in this paper, it turns out we interpreted with something that we will look at in more detail in the following slides. It's called the intermediate process, and we'll get to what that means. But you understand now what anomalous abundances are. All right. Now let's look at the stars in the early universe. And generally speaking, what you need to know is that as we go to low iron abundances, if we look at all of the stars, like halo stars, metal poor stars, and we select for low Fe over H, low iron abundance. So these stars here would have -4, would have 10,000 times less iron than the sun. Okay. It turns out this diagram shows the fraction of stars that have carbon enhancement, where the carbon over iron ratio is larger than in the sun. So although the carbon overall is less than in the sun, it is more compared to iron than in the sun. So these are the carbon enhanced metal poor stars. And that fraction really does go significantly up. And if you look at low enough iron abundance, if you look at the early universe, almost all metal poor, almost all stars that you can observe have a carbon enhancement. So that's another thing that says that something was different in the early universe. Okay, so now let's look a little bit more detail beyond carbon. How do some of these carbon enhanced metal poor stars look like? And I'm going to go straight to sort of the key point. There's lots of different types of stars. I'm showing you here an abundance distribution of one of the most mysterious ones, the prototype of one of these CMP stars that really has caused us trouble for many, many, many years. First of all, you can see in this bracket notation, we can see that all of these heavy elements, right, ignore the lines for now, are at 2.5 dex. So this means that the barium to iron ratio is 2.5 dex higher than in the sun compared to iron. Okay, so on average, all of these elements are 100 times more abundant compared to iron than in the sun. That's already very anomalous. Okay, so we need to really understand what has made this. The other thing that this means is that we're looking at individual, the fact that these all of these heavy elements are so high compared to, say, zirconium or other things, means that we must be looking at some individual site. We must be looking at an individual process that has done this at low metallicity. Because again, if everybody had done it, if this was sort of the average, if this happened all the time, that's what the sun would look like. Okay, so we're looking at a rare event. Now, there's literally dozens and hundreds of CMP stars now known, and one of the earliest classification was just saying, if the barium over iron abundance is larger than 1, and so then we have a lot of S process, of course, right? But also if barium over europium is larger than 0.5, which means that, remember, europium was an R process. If barium over europium is larger than 0.5, we call this an S process. But there are stars, they figured that out 20 years ago, where barium over europium is between 0 and 0.5. And those are somehow between R and S. And this is the prototype. What you can see here are 2 attempts to explain the star by a combination of R and S. And the problem are, these are R process elements. This is S process. Here is europium. If you just take an R process, if you just take an S process, you don't get europium, but you need europium. So you add some R process, and then you add too many of these. So the overall, you can see a combination of R and S, let alone trying to come up with an astronomical scenario that makes these, was not satisfying, was not successful. Okay, so the next slide here summarizes the problem. We have several of these CMP stars that immediately appear to have a signature of both of elements that are classified previously as dominantly from S or from R. So that's a problem. What can we do about it? So people came up with all sorts of funny scenarios, and none of them stuck. Like have a pre-R process enriched cloud, then form an AGB star that makes S process. None of that was really satisfactory. About 10 years ago, a little bit more, we just explored something. We said, let's take a nuclear network calculation and let's just run for neutron densities between this S and R. And what we found is that without knowing where this would necessarily take place, you can see that if you just do the nuclear network calculation with a neutron density where you're a little bit away from the value of stability, but not quite as far, you can really reproduce this pattern observed in these metal poor stars very, very well, surprisingly well. Especially you get high barium and you get sort of these osmium iridium abundance is low, but you do get europium. And so that was quite promising. We also noticed at the time that barium over lanthanum, that ratio was high in some of these stars, and that was maybe a special thing that needed attention. Okay, so this was the picture before R and S process, and now what we're entertaining is the new process of capture, the intermediate process. And you can see here are these little network calculations. This is an R process going way out to the value from the value of stability. S process stays closely, but the intermediate process goes sort of 2 to 6 away. And that's just because somehow we're saying, what if you had a site that made neutrons a little bit more than S process at a higher rate, but not as extreme as R? And I just want to sort of show you here a little bit. This is how we do these. This is a simple network calculation. We solve essentially for each isotope an ODE. It's a couple of systems of thousands of ODEs. And on the right-hand side are the source and sink terms, which contain the nuclear production and destruction for each isotope. And we run it in a way where we're prescribing the neutron density. And so we're starting just with iron, and then we're feeding back lead-209 into iron in some fashion that makes sure that we can just insert the neutron density and essentially solve for the equilibrium solution. I mean, this is a set of linear algebraic equations. You could just solve it directly, but we use our network solver to arrive at these equilibrium solutions. So this is a time evolution of a lot of these species. And then when nothing changes anymore, that's our equilibrium solution. And it says basically in a local sense that wherever you are, the conditions, the nuclear physics conditions in that part of the chart are then decayed back to the value of stability. And we ask, what would an elemental abundance look like? I'm going to show sort of elemental ratios from these equilibrium simulations in the next slide. But before, so this is a busy slide. I need you to sort of follow along. So the first thing that we want to do here is this diagram here shows the elemental ratios of barium and europium, which we have met before. Europium was the R process indicator, barium was the S process indicator. And let's just sort of, for a moment, consider the distribution of stars in the vertical direction. And I have highlighted in the same color here the criteria. So according to this classification, barium over europium, all of these stars have high barium. Barium over europium larger than 0.5 would be these guys. And this is what was classified as, oh, has probability S and R. Is weird. Right? Barium and europium are both present. And so you can see that most of the stars, so this is a compilation, the Gina Bayes and Fable et al. Put together. Apologies for I didn't put the reference here properly. But you can see this is a representative distribution. So we do see stars down here. These are the CMPR stars that really have our process well done. They're dominated by europium, right? They're very small barium europium. But there's lots of stars up in this regime, and there are some in this regime. But now have a look at the other axis, the barium over lanthanum. And I mentioned to you that we had noted that some of these stars that had sort of these weird features have high barium over lanthanum. What you see is that all of the stars, but especially those up here, have also high barium over lanthanum ratios. And if we check with our equilibrium simulations, if we do these simulations and we do them for S process conditions, we get these solutions. So these colored dots here are all individual equilibrium neutron density simulations where the color indicates what the neutron density was. And so 10 to the 6, 7, 8, 9 represents S process. So this is sort of the closely value of stability. We also know the nuclear physics very well here, okay? So there's no way to move these around. This is what we can get from S process. And down here is the highest neutron densities. This is the type of solution that we can get for our process. And what you note is that if you have any mix of S and R, you can go between these two lines, but you can't get here. It turns out that when you do these equilibrium simulations, and they're just asking what is possible in terms of the nuclear physics. How does the nuclear physics that is going away from the value of stability, how does that decay back to the value of stability? You can see that you find these solutions all the way up here, exactly where the stars are. And so when we saw that, we felt like, wow, that's a Nature paper. But, well, I'm glad we didn't submit it. We didn't write it because there's an important detail missing. And so first of all, we have to pause maybe one more moment. The fact that we do see large barium over lanthanum ratios is a real problem. We talked to the observers. The observers insist that these ratios are individual stars might move here or there, but that there is a cloud with baryon lensum higher than 0 is now, observers have not been able to figure out why this could be just an observational problem. So we need to solve this problem. But in order to solve the problem, we need to also answer the question, so intermediate, not as process may explain most of the CMP star abundances, but where and how does it take place? And so we have some indications over the years. We came up with a scenario for this. There are some post-AGB stars that do similar things. We were guided by that. The idea is that you have something like a helium shell convection, for example, in an AGB star, in a rapidly accreting white dwarf, maybe in a massive star. And so this is schematically the helium shell flex convection. And above the helium shell convection zone, there is stable material with a lot of protons that are not yet produced, not yet burned. The protons are ingested on a dynamic time scale into the convection zone. And halfway down, the temperature is high enough for rapid production of nitrogen-13. As a matter of fact, the nitrogen-13 has a half-life, which is about the timescale of the convective turnover, 10 minutes. And so the nitrogen-13 can get to the bottom where the temperatures now are 270 million Kelvin. And when the nitrogen-13 decays to carbon-13, it will immediately release a neutron through this carbon-13 alpha N reaction that I mentioned before. So it is this dynamic nucleosynthesis on a convective, where convection and reactions are interacting, where we can create a combination of producing the carbon-13 very rapidly and releasing the neutrons much faster than an S process, but much slower than in our process. There is some more slides here that explain this. I want to skip them. We have done these hydrodynamic simulations that describe these entrainment processes, which sort of back up the scenario that we have here. So the hydrogen is ingested here. This is a big 3D hydro simulations of such a situation. This is the hydrogen coming in. Here is the vorticity. And you can see that the hydrogen is disappearing as these plumes are going down. And then we have ways how we can post-process scenarios like this that I can't go into detail. One of the astrophysical sites where this can take place are these rapidly accreting white dwarfs. Think nova, but at a much higher accretion rate. And they do helium shell flashes, and they do repeated helium shell flashes. And you can do a hydrodynamic simulation. I don't know how well the movie comes across over the internet, but you can see here one of our hydrodynamic simulations where on the left, you see a still image of the ingestion of protons, and on the right, you see is central plane slice of vorticity. And so this goes on for some time. And if I switch sort of movie versus vorticity, you can see here the color bar is indicating the abundance of hydrogen-rich material. There's lots in the stable layer above. And as this hydrogen material is ingested into the convection zone, it is burned, and then ultimately we can see how the hydrogen that is releasing energy through reactions with carbon-12 is ultimately feeding back into the convective flow. And in some cases, you can see non-spherically symmetric instabilities that have the potential to really rip apart the entire shell. So, you can see lots of non-spherical ingestion. And if I don't know whether I can fast forward this here, about here, you see a global oscillation. We call this global oscillation of shell height ingestion. And this can actually be so dynamic and energetic, depending on the parameters, that this will rip apart the entire convection zone. It might lead to mass ejections. It might lead to very extreme termination of this particular convective reactive scenario. We have a way that I can't explain in detail to post-process such hydrodynamic simulations, but I'm going to not explain this unless you ask me at the end. But I want to sort of have the last 2-3 slides to sort of connect it to dynamic, because there's one final leftover detail that is really key. This diagram again shows essentially the barium rhodium versus barium lanthanum diagram, with these each star being sort of the observed abundances. And here you see again our CMP S stars, the CMP I stars, where we now think that all of these are CMP I, maybe except a few up here. You can see some simulation predictions. The crosses are these one-zone calculations that I showed you before, the equilibrium calculations. And you can see that some of them can get actually to very high barium over lanthanum ratios for neutron densities that are just right, 14.5. But if we do the nucleosynthesis in the hydrodynamic or multi-zone, 1D multi-zone simulations, even the ones that have these high neutron densities end up having low barium over lanthanum ratios. And our models are agreeing with models, for example, by Arthur Choplin, who has a maximum neutron density, which is even higher, yet this red star, they place their result here also at barium over lanthanum of 0. So it looks as if, and we do understand this now, it's sort of this superposition internal freeze-out effect that I could explain in a little bit more detail. We understand it, we believe it. The point is that if we run this in multi-zone simulations, in the most realistic simulations, the possibility that was offered to us by nuclear physics to explain the high barium lanthanum has gone away. How do we do it? Now, what we realize now is the following. If we do these multi-zone simulations and we follow them as a function of time, it turns out that if we allow for the fact that the multi-zone simulations are not always proceeding into a convective reactive equilibrium, but that at some point in time, the feedback, the global oscillation of shell hydrogen ingestion that I've shown here from another simulation where it really gets going, the hydrodynamic feedback is terminating the whole thing and blowing it apart. We can see these are simulations, the time evolution of a multi-zone simulation with the high enough neutron density. It goes all the way out here, and then it comes back. And these different stars along this track can be interpreted as events where this convective reactive nucleosynthesis has been dynamically terminated at different times. And that is what we think is the solution to explain these high barium over lanthanum ratios. And we think that these results are essentially the smoking gun for the dynamic convective reactive nucleosynthesis of heavy elements in these metal poor stars. That is the punchline. I have some more slides here that show you some movies, and instead of having a summary, which I do have somewhere as well, I just thought I stop here and I leave you with this movie. I don't know how well it shows on your screen. It shows very well on my screen, obviously. It shows this is a low velocity asymptotic giant branch star hydrodynamic simulations with 2 color bars where, again, we see the ingestion, these red, yellow, blue color scale is the hydrogen-rich material being ingested, and the flaring up yellowish brownish color scale is the energy generation from carbon-12 p gamma. So you can see how at the end of these tails of these curtains that are coming in, the energy generation is very non-spherically symmetric. It destroys the hydrogen, and it will, in the simulation, ultimately lead to another example of such a global oscillation of shell hydrogen ingestion, which is key to terminate the I process. Here you go. Terminate the I process nucleosynthesis and sort of put a stop to it to reveal the non-equilibrium convective reactive solution in the observed stars. This thing ultimately does another one, which blows it up to the extent that we couldn't follow it anymore and the simulation is over. Okay, nuclear reaction rates are important. You can ask about it if you want. This is the key point. Convective reactive nucleosynthesis is just one example. There are others where we feel this is important, but thank you very much. That's sort of my bottom line. And I think it's more fun if I just go back here and play this movie again. That's it. Right now I can't hear you.
You can't.
Oh yeah, yes, now I can. Okay, yes,
We're
yes, I
just
can.
quiet. Okay, all right. Questions? I have a warm-up one, which was just 1D versus 3D. Back in grad school, I remember being suspicious about one-dimensional stars because sure, they're roughly spherical. But I was always wondered, were they really spherical, and could you really treat them as one-dimensional? But these simulations that we're watching right now are just radical. I mean, you'd never be able to treat this one-dimensionally. And so I'm wondering, did you expect that level of turbulence and non-sphericity?
Yeah, so these simulations, I should say, these simulations, of course, we're doing, you mentioned it in your introduction, are done with our PPM star collaboration, and the author of the PPM star code, Paul Woodward at the University of Minnesota, of course, is sort of the key person here who is enabling these type of large-scale simulations. I should mention that explicitly. We are collaborating for 10, 15 years now, 20 years maybe, on these types of simulations. So obviously, 1D solvolution has been extremely successful in answering many questions and reproducing a lot of exciting, interesting observations. The interaction of convective motions, the convective mixing of different types of fuels, and with the energy feedback from nuclear reactions is indeed something that we're now exploring. And this is an example of where this how this looks like. I did not expect this. We first came across this type of problem when we studied post-AGB stars and the hydrogen ingestion and things like Sakurai object, and where we tried to explain the PG1159 stars. And they're sort of, it's the old Equilibrium Detlev Schoenbrenner born again scenario, where a post-AGB star would do a final helium shell flash, and because the hydrogen burning shell has already stopped, the helium shell flash convection zone can mix into the hydrogen-rich layer, bring down hydrogen, and then have this rapid, real-time, born-again evolution as we have observed in Sakurai's object. So it turns out that the equivalent of this global oscillation of shell hydrogen that we introduced in an APJ letter in 2014 was was known in 1D evolution as the so-called split of the helium shell flash convection zone. So there are studies going back all the way into 1970s where this was first discovered. And so in 1D, the cell evolution does respond by just saying, oh, where the mixing, if you introduce time-dependent mixing, where the time-dependent mixing time scale is equal to the carbon-12 p gamma reaction rate, that's where we suddenly produce an entropy jump. And this is where a new convection zone starts. And so the little entropy jump means that there's a small separation between the two convection zones. And so cell evolution calculations have found that for decades. What we, of course, do not know and cannot know from 1D simulations is what is the actual response to this? How does the interface look like? Is there mixing possible between the two convection zones? Is the convection zone so energetic that because it creates these global instabilities, it might actually blow up the star? Under which conditions? So these are all things that we need to do these 3D simulations for. And they do indeed open up these convective reactive nucleosynthesis pathways that really may be responsible. Sorry, here, this is what I want to show. So there is various examples where we think that some of the unsolved problems in nuclear and cell evolution may be related to these to this picture that you have nucleosynthesis in different charts of isotopes, but then you also have mixing which means that things that are produced somewhere could, on the nuclear time scale of that process, appear out of nowhere into a new layer, so to speak. And so we call that sort of another dimension to nucleosynthesis in a sense. And yeah, so that's what we can only do in 3D hydro simulations. And what is also interesting that in massive stars, for example, where we explore this in the context of oxygen carbon shell mergers, not only can we produce some elements which are otherwise not so easy to produce, but these shell mergers and three-dimensional effects would also, of course, have consequences for the pre-supernova structure and the supernova explosion that really would go through a different type of progenitor, 3D progenitor, ideally.
Mm-hmm. Yeah. Maybe one more short question. It could be an easy one. Yeah.
Hi, Herwig. Thank you so much for the great talk. So I have a quick question, not exactly about stars, but about a stellar population. So sometimes in stellar population, we also see like anomalous abundances for different kinds of elements. So do you think like those kind of anomaly can also be explained by like a different nucleosynthesis model, or do you think like there are other important factors like galactic veins or quenching or maybe something else like ISM plays a more critical role in that?
I think this is something that you that has to be answered on a case-by-case basis.
Okay.
We have worked with Benoit Coté for many years in the GINA context, and he has some papers where he looked at if you know the galactic chemical evolution for enough elements, and where enough is whatever he had used at that time, which is 10 years ago, can you reconstruct, for example, the parameters for galactic chemical evolution in a relatively simple galactic chemical evolution model? And the answer was the bottom line. I would have to go back and read the paper, so apologies if I'm not 100% correct in producing that result. But what I remember is, even if you had a number of elements, it was very, very difficult to really inverse the problem and constrain effectively the galactic chemical evolution parameters. Conversely, there were obvious problems in the yields that no galactic chemical evolution model or assumption could correct. So what you're seeing there is that if the nuclear yields are wrong, if you're starting with the wrong production, you can't fix it with galactic chemical evolution, which is good. It will show up. It's good, but also the other way around. Constraining galactic chemical evolution with chemical abundances alone is also not obviously possible.
All right, thank you.
Yeah, thank you. Looks like our speaker, we're out of time. Thank you, Falk. We're gonna truncate. There's another class coming in.